welcome to day 7 of the 12 days of LiDAR. My name is Alex Billick, and today we're going to be talking about QGIS and LiDAR. Before we dive into QGIS as it exists today, I wanted to show you something. This is a bit of a historic deep dive, but this is actually the title slide from a slide deck that I made back in 2010. At the time, I was working on a special topics in Masters on open source GIS and whether it could or could not replace ArcGIS at the time. The intent was really to figure out what space open source GIS was filling. And so what I did was I took all of the data that was available for our second year GIS class and said, could I execute those labs in Quantum GIS, QGIS at the time, and see does it actually work? Let's look at some of this data because when I looked at it, it made me laugh and I had to share it with this group because I think that these folks that are listening to this video series might appreciate this. So in 2010, I had a very modern Toshiba Tecra 8000 with a Pentium 2, 256 megabytes of RAM, and a 10 gigabyte hard drive. And I was trying to see if I could execute any kind of GIS in this open source software. At the time, it was version 0.11 of Quantum GIS, which would later become QGIS. And it really does kind of feel like a quantum leap. If you think about that, we're talking about a time span of 13 years to go from 256 megabytes of RAM to 128 gigs of RAM in my computer. A 10 gigabyte hard drive being the less than a fraction of the size of a USB stick. I mean, the speed of technology is massive, but the speed of open source technology is even faster. So if we open up QGIS, the reason that QGIS is able to move at the speed it does is because of its decentralized model. We have groups like Lutra Consulting doing fantastic dev work where they crowdsource and then they execute, bringing features to a tool set that is used by a wider range of audience. What I'm going to do is add in the unclassified data. So as I downloaded it from the Ministry of Natural Resources, LiDAR data for the Lakehead campus. And you see it loaded very quickly. All the data in Ontario has already been calculated for what's called CEOPC. I talked about this briefly before, but it's Cloud Optimized Point Cloud. If it wasn't, you would see sort of a red bounding box and you'd see it would do some calculations. We'll probably see that later on in the example here. But all of the data in Ontario, no matter where you download it from, will operate this way. So the second we open it, it defaults to classification. If we right click on it and we go to the properties, we can actually examine a lot of different information. So on information, we can see the projections, we can see how was it processed last, all kinds of different things. Symbology, we can go to attribute by ramp and we could change this to the Z values, for example. And what that's going to do is represent the elevation values on campus. So we can see how things ramp up here. I'm going to change it back to classification, but you can experiment. What's interesting with this is we can actually change how this layer is going to behave in 3D. So when we look at this layer in 3D, we could actually either have the 2D symbology be sort of that's the symbology that follows through the entire software suite, or we could have it do something different in 3D. So I do appreciate that. What is most useful to me, though, is looking at statistics and being able to dive in again to understand what is the breakdown of this image by each class, what is the maximum value and what is the mean value in different respects. It's a very useful natural language way of reading this information, so I appreciate that. Now, looking at this, we've got a lot of information here. Again, buildings are called vegetation here, same as they were before. But in the processing toolbox, which is kind of like the ARC toolbox, we've got 3 different things here. We're going to open them all up and take a look. We have point cloud conversion, we have point cloud data management, and point cloud extraction. What we can do is we can export some of this information to a raster to make it more usable. So we're going to do that right now. We're going to say, okay, our base LiDAR data, what we're actually going to export out here is the Z value. But what I'm interested in is not just the Z value. I'm interested in the Z value where the classification equals ground. So a DEM. Using this tool, I can say, take my base point cloud, read the elevation values, and where classification equals ground, give me a raster at a 1 meter resolution, which is what this is. So we'll save this and we'll call this DEM of campus and say save and run. And we'll take a look at the results here that are generated. Now, I'm not having to code anything. I'm not having to pass any variables. I'm not having to do anything else. This is all being done in QGIS, which is very handy. Takes a second. There we go. And we turn that off. And now we see, obviously, some things are missing. It's not going to fill in where buildings are. We can deal with that in a moment. But we can go into properties, and we can change this to something like hillshade and actually see what's going on campus. And that's a very powerful thing to be able to do with very little input effort. Before I get into any of the extensions within the toolbox here of how we might be able to fill these gaps in and everything else, I want to highlight something. Over the next 2 days, we're going to be talking about two other suites. One is Fusion and one is the Last Tools. But within QGIS, we can actually plug into those two tool sets. You see here that we have Fusion and we actually have Last Tools as well. This is what makes QGIS so powerful. We actually can bring in our own R scripts if we want to. We can extend this tool set so that if we have one programmer or two programmers on staff, we can build tools using high-level programming languages and then make it so that any analyst can actually execute those tools. QGIS makes that really easy to do. And so when I'm talking about Fusion and I'm talking about Last Tools, I want you to remember the fact that we could execute a lot of those tools from within QGIS with zero additional programming skill. So that's really powerful. All right, how do we fill these gaps in now? Well, what we're going to do is we are actually going to first take a filter. So point cloud extraction, we're going to do a filter. So our input is our raw point cloud. Our filter expression is going to be where our classification equals ground. And we're going to call this a ground LiDAR.laz. Whatever you want to call it. So what I'm doing right now is I'm extracting a portion of the point cloud that just represents ground returns. You could do other things in GDAL to fill these gaps in and everything else. I'm showing you one workflow. Okay. So now the only thing that you're seeing is ground LiDAR. And you notice that, well, I completed too quickly, but you may have noticed that it was computing things there. It was this red bounding box, and now it's filled things in. It was computing the COPC support files. Once it finished, we've got our ground returns. Now what I want to do is export to raster using triangulation. And using this tool, putting in our ground LiDAR, again at 1 meter, I could use a filter expression here, but we don't need to because we've already done that. What we want to do is say the Z values in this particular case represent our ground LiDAR. So we're going to save this as DEM of campus. I'll call it 2. Or actually, I won't call it 2. I'll call it 10. And this might take a little bit longer because it's going to try and fill those gaps in. But what we want to do is understand the fill in those gaps of the building so that we've got a wall-to-wall DEM product here. There we go. And it completed. And there is our DEM of campus. And again, we can go here to Hillshade, apply OK, and we've got some good results. So I'm turning everything else off. I'm going to show you something else here. If we duplicate this layer and turn it on. So there's our Hillshade. I'm going to go in here, and I'm going to say, instead of Hillshade, we're going to use a single band pseudo color of the elevation values. And if you use this and you say the blending mode is actually multiply, it will take the underlying hillshade and give you that shaded relief effect, which is very powerful. So now we can see a color, and a context to everything going on campus here without the buildings. And we've done all of that. QGIS is more than just a viewer. QGIS is a full spectrum LiDAR processing suite. We can actually do a lot of different things here. If I wanted to compute some of those LiDAR metrics, for example, that we talked about, so point cloud analysis, I want to do cloud metrics. So let's say these were my plots. You wouldn't normally run this on the entire thing. You'd run it on just the plot data, but we're going to do this for example. Use the 64-bit because we've got a faster computer. First returns only. I want the detailed output. Sure. I'm not looking at this too carefully, but above 2 meters with a minimum height of 2 meters. We're going to call this cloud metrics.csv and run. What we're asking it to do is treat this entire thing. If we were doing this by plot, we would have given it a subset where each individual point cloud represented one plot. But I'm leveraging a tool set that you're going to learn more about tomorrow within QGIS without having to do any command line. And that's a very, very powerful thing. All right. So it's taking a moment. I mean, it's a lot of points that it has to reference through. But once it completes, we're doing all of this within this framework. So far we've looked at a understanding of what the ground looks like. We've figured out how to be able to create useful raster products. Now what I want to show you once this completes is how to look at the data in 3 dimensions. And that will show you the full suite of what QGIS can do. But I highly recommend that you download this and you try it out to understand exactly the power of QGIS and point cloud data in 2023, because this has come a long way in a very short amount of time. And there we go. So that was cloud metrics. And what we generated was a very quick understanding of all these different metrics. And if we had divided this up by plot, we would have different percentiles and different elevation values. This is not height normalized. It's not ideal. I'm just showing you an example of how to look at this data. You can also go to View, New 3D View, and actually look at this in 3 dimensions. So we've got the same data here. So I want to turn on my point cloud and maybe turn off the other stuff. I'll leave the campus tin on because that's of interest. And it looks blue. This does happen sometimes. What you have to do is just go in here to our point cloud and just kind of remind it to say follow 3D view. And when you do that, the 3D view comes through, and then you can zoom in and you can actually look at this information in 3 dimensions. And that gives you an example of what is possible. The last thing I want to show you here is under View, Elevation Profile. There's a little line here. It says Capture Curve. We're going to draw a line across here, and then right click. And it lets you pull that same 2D profile. But what I really like about this, that other tools don't allow you to do, is to interact with those DEM derivatives as well. So you notice that here, I can turn off that tin, for example, that we created. And you can see that the tin fills in those gaps. This is not something that other profile tools can do, at least not that I've seen. So I find this incredibly useful. I have generated very rapidly wall-to-wall inferred tin which fills in the gaps. I've pulled up the point cloud. I've looked at it in 3 dimensions. I've computed cloud metrics. This is a very, very powerful set of tools that is available to you. So I highly encourage that you download QGIS and you try your hand at it to see what's possible. With that being said, tune in tomorrow for Fusion LDV, and thanks for listening.